In this video, I'll talk about MATLAB's fzero function. This function is the built-in function in MATLAB for root finding. After studying this video, you should be able to use the fzero function to solve roots problems in MATLAB. You should also know how to set options for any MATLAB function that uses the optimSet command. So we'll get an example of that because fzero is one of those functions. And explain in general how the fzero function works. So here's syntax for calling the fzero function. You can call the function in two ways. One, you can call it with a single initial guess, x0. And when you do that, it'll move forward from there. And we'll talk about how in just a minute. But that's a single initial guess. And the output is going to be x, which is the root estimate. And this fx, that's the function value at x, which is at that root estimate. And if it was exact, right, fx should be 0 if it's the exact root. The actual value of fx we call the residual. So we have a less than perfect root estimate because we're using a numerical approximation algorithm. When we plug that back into our roots function formulation, we get a value other than 0. And the fact that that's other than 0, we call that a residual. That's what's left over because of the slight inaccuracies in our root estimate. A second way of calling the fzero function is with an initial bracket, similar to bisection. We call bisection method. Now when we call it with an initial bracket, it's always going to search for a root between those two numbers, x0 and x1. And note this is a two-element row vector, not two different inputs. In this case, this would be a single scalar initial guess. And in the first case, f0 is just going to converge on whichever root it lands on that's close to x0, x0. So let's talk about how it works. If you have a single initial guess, what fzero does is it starts with what's called an incremental search algorithm. And it's a fairly simple idea where we can just imagine it evaluates the function. Here's our function. It evaluates the function from that initial guess, x0, at several increments and keeps stepping along until it says, oh, okay, right there I have a sign change. So here we got a sign change in the function. Let's go to step 2. It'll also start at step 2 if you give it an initial bracket. So now it knows that it has a bracket with roots in between, and it's going to start a bisection iteration. We've spent plenty of time with bisection, so hopefully you understand how that works. And one of the things we've seen with bisection is it's guaranteed to converge as long as that initial bracket has a sign change, but it is slow. So it goes until it gets close to the root, and then as soon as it gets close to the root, it changes to two faster open methods. It uses the secant method, which we've also talked about. That's where if we have two values, two guesses on that function, and we'll take a secant line, draw that through, and our next guess would be where that line crosses the x-axis. It also uses something that we haven't talked about, and that's called inverse quadratic interpolation. And it's the same basic idea conceptually as the secant method, but it can, for certain functions, be even faster because it uses 3 points, 3 previous guesses on the function, and fits a parabola through those 3 points and uses that place where the parabola crosses the x-axis as the next guess. And you see in this example how that next guess is quite a bit closer to the root here. And for certain functions, that inverse quadratic interpolation will be even faster than the secant method, because recall our idea for Newton-Raphson and the secant method was, let's take advantage of something about how the function is behaving. In that case, it was the slope. Now, with inverse quadratic interpolation, we are informing our guess, not just with the slope, but with the curvature of the function. And so using that to inform the next guess can accelerate convergence even faster. So it'll start with an iteration. It's beyond the scope of this class to talk about how fzero decides between the secant method and inverse quadratic interpolation. We can think of the secant method as a linear interpolation to get the next guess. So it's two different interpolations here, and how fzero decides is beyond our scope. But it basically looks at the way that the function is behaving and the way that the approximate relative error is behaving with the next guess to inform that choice. If it starts to diverge once it's moved to that open method solution, it will revert back to a bisection and an incremental search and bisection to try and get back on track and find that root. So let's look at some options for controlling fzero. One thing about fzero is we pass options to the function through the options data structure, which is set with the optimset command. And this is something that is common for a lot of MATLAB functions, and here's the first place that we've seen it. We basically lump all of the possible options into this third input argument called options. And the way that we set values in that input argument with the optimset command is these parameters here, and sorry for the confusion, but MATLAB calls them parameters, even though we've also been talking about parameters in a different context with mathematical modeling. In this context, the parameters are what is the option, and two common parameters are display, and if you set that to iter, I-T-E-R, fzero will display how it is calculating each iteration and what the current root estimate is at each iteration. Another common parameter is tall x, and that is basically the stopping criterion, epsilon s. So we saw before we want to have some explicit control over what that stopping criterion is, and tall x is what allows us to do that. And we'll see an example of the syntax of how to do this in just a second. But first let's talk about that other type of parameters, and those are the parameters in a mathematical model. And recall what we did with our root finding functions that we developed is we used the var arg in variable to pass multiple parameters through a function. fzero doesn't let you do that, but the way to do it is to parameterize the function as you send it to fzero in the input list. And below here is a section of code that illustrates how you would do that. So here's the original function definition in line 18. Here's using the options to set epsilon s equal to 1 times 10 to the minus 6. That's how we would set those options, and then that options variable is passed as the third argument, third input to the fzero function. And now the first input here, what we're doing is we're parameterizing our function fun by generating a new anonymous function that's just a function of x. By evaluating, what we've done here is evaluated fun for the current parameter values there. And those current parameter values for this, each iteration is 1.0, which is the value of Ka, and the indexed value of KB. If you recall back to this example, this is that same contaminant model analysis that we've been talking about. What we're doing here is looping through various values of the parameter KB and calling fzero for each of those values. So that code here is included in this video folder, and I would encourage you to download and study that code, step through it with the debugger, and make sure you understand how this code is working and the syntax of using fzero. And that concludes this video.